All right, so everybody take a minute to complete today's daily quiz, and then we'll move on here to our new chapter, chapter 16. All right, so first of all, next week, right? Next week we got our first exam on chapters 14 and 16. Chapter 16, this one that we'll start today, is a little bit shorter of a chapter, so we'll be able to finish that off by Friday. It does have one more like algebraically complex component, so everybody needs to make sure to bring their calculators tomorrow, all right, on Friday. It'll be a big kind of calculation day. Next week, you'll have Monday or Tuesday to take your exam in the Bulldog Testing Center. Make sure that you have your student ID, right? So if you've lost your student ID, you're going to have to get a new one to take it in the Bulldog Testing Center. On Monday of that week, since we have this nice morning class, Monday morning we won't be learning anything new. I'll just use that as an opportunity to review some of the old stuff for that exam. The intention being that then you'll go take the exam either after that class on Monday or the following day on Tuesday. Okay? So today we're going to be starting on this concept of equilibrium. This is going to be an important concept. We're going to see it revisited over and over and over again in future chapters. Okay? So up until this point, a lot of the reactions that you guys have studied, you kind of assume that these reactions go 100% to completion. Right? So reactions that go to completion. So for example, let's say we're just going to take like a generic reaction A being converted into B, okay? So if we made this graph here of reaction progress, or we can even say concentration, over time. All right, at the beginning of this reaction, everything would start off as A, right? And how much B would I have at the very beginning of this reaction? None, right? Okay? And if this reaction goes 100% to completion, that means that over the course of time, every single bit of A gets consumed. And all of that A is then converted into the product B. All right, so if a reaction goes to completion, that means 100% of the reactant is converted into product. All right, and so up until now, when you were predicting predicting how much product was formed using stoichiometry, you were sort of under this assumption that these reactions go 100% to completion. And for some reactions, that's a pretty freaking good assumption, right? A combustion reaction is a very efficient reaction where just about 100% of reactant is converted to product. So there are some reactions that this very simple assumption that everything goes to completion is a pretty good assumption, okay? But it is sort of this overgeneralization because there's no such thing as a reaction that's 100% efficient, okay? So again, good assumption, good generalization, not strictly true. And for some reactions, it's a terrible assumption, okay? So there's some reactions that go to what we call a dynamic equilibrium. For a dynamic equilibrium, we would represent that instead of using this one-sided arrow right here, we actually use this double-headed arrow. So now A in equilibrium with B. Oh, bummer. Okay. And so if I were to draw this same sort of graph for this reaction here, again at the very start, I got everything is A and I don't have any B, right? And as we would expect, the concentration of A will decrease over time and the concentration of B will increase. That was terrible. But the difference is not 100% of A gets converted to B. There's still a little bit of A left over, which means that not 100% of my mixture is product, right? So a dynamic equilibrium simply means that not all reactant is converted to product. All right. And sort of this portion right here of my graph where these concentrations have stabilized and are no longer changing, this is what we call equilibrium. All right, so the definition of equilibrium means that the concentration of all products and reactants is no longer changing. Okay. And you can see we call it a dynamic equilibrium because there's still an appreciable amount of reactant left over, right? So again, that assumption that everything went to completion, it would be a horrible assumption in this case. Okay. Now, importantly, it's not just that this reaction, let's say that this is like now 20% A, 80% B. It's not like the concentration of reactant decreases to 20% and then all those molecules get together and decide, all right, we're done. I'm cool here. Okay? What happens at equilibrium is that the rate of the forward reaction meaning A going to B is equal to the rate of the reverse reaction. Right? So the reverse reaction meaning that B is being converted into A. Okay, so again, not how we're used to thinking about reactions, or at least not how you guys were introduced to thinking about reactions. Previously, the idea was that reactant gets converted to product, and that happens 100% efficiently, right? It turns out that with every reaction, yes, you will have reactant get converted to product, right? A going to B, but there's also going to be a small population of that product that gets converted back to reactant, okay? And that is when equilibrium is reached, when the rate of these two events are equal to one another. So I have as much reactant falling apart into product as I have product combining to be a reactant, right? So the rate of these two reactions in either direction are equal to one another. That's when equilibrium is reached, right? So again, it's not like these reactants get to a certain percentage and say, all right, I'm done. We're all just going to stop reacting and everything's going to remain constant. There's back and forth going on, right? It's just that now the reverse reaction of B getting converted back into A is now equal to the rate at which A is getting converted to B. Okay, what's up?
Is it like a vice versa? Like A equals to B, B equals to A?
So it's like one direction A is being converted to B, the other direction B is getting converted to A, and those are happening at the same time. Okay, and the analogy in your book, which is a pretty good one, is it's kind of like how the population of each country remains relatively constant over time, despite the fact that we have people coming and going at all times, right? It's just that the amount of people traveling from here to the UK versus the people traveling from the UK to here reaches some sort of an equilibrium where our populations aren't changing over time. Okay, so bottom line is the rate at which this forward reaction happens is equal to the rate at which this reverse reaction happens at equilibrium. Right, this dynamic exchange at equilibrium. Okay. So now what is definitely going to be probably the most important concept for this particular chapter, because we're going to see it over and over and over again in future chapters, is this concept of an equilibrium expression. Okay, so I'm just going to do like a sample reaction here. All right, what we're going to be able to do is to construct this formula that defines the equilibrium of this reaction in terms of what's called K, an equilibrium constant. And kind of simply put, K relates the concentration of products and reactants at equilibrium. And remember, those concentrations aren't changing at equilibrium. Okay, so this expression will equal to this constant value, this equilibrium constant. And you don't know how I'm getting this expression yet. We're going to get there, all right? But for each reaction, there's going to be this unique equilibrium constant that you can find, which is very helpful because then we can tabulate these values into tables, right? So back in my day, there were gigantic books in the lab. Nowadays, it's all online in databases. But nonetheless, for your particular reaction, you can go and you can look up an equilibrium constant. and that will relate the concentration of products and reactants at equilibrium, right? So what we're going to remember for our equilibrium constant, okay? Every time you go to build your equilibrium constant, you're going to chant this into your head. Products over reactants, okay? It's going to relate the concentration of products divided by the concentration of reactants. So products over reactants. That's what you're going to say to yourself every time you go to build an equilibrium constant. So now let's use this particular example here. I'm going to actually move it down. All right, so how do I build my equilibrium expression? I got this constant K. It's going to be equal to the concentration of the products, in this case my HF, divided by the concentration of my reactants. So in this case, I have F2 and H2. All right, so before we go on, just convince yourself that we indeed have our concentration of products over our concentration of reactants. What's up? Because it's going to be the product of those. We're going to see that our equilibrium expressions are always multiplication and division problems. There's not addition and subtraction, right? So yes, you're right. Up here I'm like combining these, but when I go to build my equilibrium expression, it will always be multiplication of those reactants together.
Do we ignore the moles like on the product side it has 2 HF whilst on the reactant side there's only 1? Like the moles
So we're going to get to this coefficient here in a second. I'm not quite done yet. I just want to make sure that we can all see that we're products over reactants at this point, okay? Absolutely. Now, all of a sudden, there's one more thing we got to do, and this is kind of a weird thing about building equilibrium expressions. We have to start with a balanced chemical equation, because in our equilibrium expressions, these coefficients are going to become exponents in our equilibrium. All right, so coefficients become exponents in our equilibrium expression. Okay? So again, this is an expression that relates the concentration of reactants to the concentration of products at equilibrium. And kind of the magical, amazing thing about chemistry is that it doesn't matter how much reactant you start with, how much product you start with. If you let this reaction come to equilibrium and you plug those concentrations into this expression here, you will get the same value every single time. Right? No matter how much you start with, no matter what size vessel you put it in, anything like that, you let this reaction go to equilibrium and you punch those concentrations into your equilibrium expression, you get the same value every time. Okay? That's why it's incredibly useful, right? Because then we can tabulate all these values for all these reactions, and you can figure out ratio of product to reactants at equilibrium. All right, so before we move on, because again, this is probably the most important part, I'm just going to put down 2 chemical reactions, and y'all are going to build me the equilibrium expression for those chemical reactions. Two, three. Actually, this one's fine. Let's just do this one. right, so my equilibrium constant K is going to be, again, every time I build an equilibrium constant, still to this day, I chant products over reactants to myself, right? So concentration of my product over the concentration of the reactants. And then I'm going to remember that my coefficients in my balanced chemical equation become exponents in my equilibrium expression. All right, so coefficient will become an exponent. The symbol here, you could put gas down there, but you don't have to at that point. It's just the concentration is the quantity that you're talking about. The states are gonna, you're kind of like skipping ahead on me here. The states are gonna be very important. I've been conveniently using reactions with gases for a reason, and we'll talk about sort of what happens when there's a solid or a liquid here in a second. But yes, good question. But yes, for right now, just worried about constructing that equilibrium expression. Again, you got the concentrations of your reactants and products, and your exponents, or your coefficients, become exponents. Okay? All right, so before we get to the states business here, there's one thing we're going to do, and that's just take a look at the value of K and what that says about a particular reaction. Okay, so if we just have a simple reaction where reactants in equilibrium with product, right? We build our equilibrium expression, product over reactant. Okay, so let's say that for this particular reaction, we looked it up and K was this very, very large number. All right, so let's say that K was equal to 10 to the 10 or something like that, some enormous number, right? Would this favor the reactants or products? Why products? Exactly, right? So if K is some huge value, like 10 to the 10, that means that this number is really big and that this number is really small, right? So a large value for K would be a reaction that favors the products. Okay, a reaction that goes very close to completion. So this would favor the products. And what about if it was the opposite? My value for K was 10 to the negative 10. Is that a reaction that's going to favor the products or the reactants? The reactants, right? The exact opposite argument. So now this is very small. My numerator is very small. And my denominator is very large. That's the only way I'm going to get a value of K that's a teeny tiny number like 10 to the negative 10. So this would favor the reactants, which is just a fancy way of saying it doesn't really happen. Right? A reaction that favors the reactants means you're going to mix these two things together and absolutely nothing's going to happen. It's not going to form any product. Okay? So we can kind of have this little range with regard to K. Okay, generally speaking, we sort of use these rough numbers here. We say that if K is between 10 to the negative 3 and 10 to the positive 3, this is what we would call that dynamic equilibrium range, when there's an appreciable amount of both reactants and products in that solution or in that mixture. what we call an appreciable or a non-negligible amount of both reactants and products. All right, if K is greater than that 10 to the 3 value, that again is a reaction that favors your favors your products. Right, or on a reaction that we could pretty reasonably say goes to completion. And if K is smaller than that 10 to the negative 3 value, then we say that this favors the reactants, which again is just another way of saying nothing really happens. What's up?
What happens if K is in the middle?
The middle range here is what we call the dynamic equilibrium range, which again means that there's a good amount of both products and reactants there. You would, depending on the exact value of K, if it's greater than 1, it slightly favors the products. If it's less than 1, it slightly favors the reactants. But there's an appreciable amount of both. It's not, you can't think about it as black and white, one side or the other. Okay? And I guess just to clarify, why do we like to have these cutoffs? Because it's much easier to think about a reaction as black and white. It happens or it doesn't happen, right? The math becomes 1,000 times easier if we can just say it goes to completion. If all of a sudden we're in this dynamic equilibrium range, we're going to see we can't just use simple stoichiometry. We're going to have to use some more complex algebra. That's what we're going to do next class. But anyways, yeah, that middle range is the pain in the butt range, right? So if you can reasonably approximate that your reaction goes to completion, your life is so much easier, right? So that's why we would bother to have these little cutoffs and just instead of just treating everything as an equilibrium or a dynamic equilibrium. All right. Okay, so now we're going to look at reactions with solids and pure liquids. Okay. And I'll just give you kind of the punchline here. Solids and liquids do not appear in an equilibrium expression. Okay, so let's take a look at just an example here. Let's say that I was given this precipitation reaction where we mix a solution of sodium chloride with a solution of silver nitrate. And it produces a solution of sodium nitrate. And then the precipitate solid silver chloride. So now all of a sudden we're going to be paying attention to our subscripts very closely when we're constructing our equilibrium expressions. All right, so the first thing you're going to do is just like before, products over reactants. I want everybody to take a minute, set up your equilibrium expression for this reaction. Okay, so again, I'm going to do my products. Over my reactants. Okay. But then I'm going to notice that this one here, this particular one, is a solid. And importantly, a solid doesn't really have a quote-unquote concentration, right? If we're thinking of moles over liters for a solid, that's not something that's variable. It's actually, we would call it density, would be the more convenient way to express it, but it's constant for a given substance, right? So this value here, no matter what, is not going to change in this expression, right? Your solids have a constant concentration. So why are we going to even include it as a variable? We're not. So you just don't include solids or pure liquids in your equilibrium expression. So the actual equilibrium expression for this would only relate these aqueous components together like this. So again, solids and pure liquids do not appear in equilibrium expressions. They just don't have variable concentrations. Okay, so then let's say that we had I want you guys to build me our equilibrium expression. Whoops, this is AQ. Build me our equilibrium expression here. Okay, so I got my products. Over my reactants. Nope, that's not true. Oh my gosh. Okay, but then which one of these terms do I get to exclude? The H2O, right? That pure liquid water that's formed. Water's concentration is a constant 55 molar. I'm not going to include a constant in this expression, right? So that will just drop out. And so really it's that concentration of the Na2SO4 over H2SO4. And importantly, that sodium hydroxide concentration is squared because my coefficient becomes an exponent. What's up?
So you want us to go from the H2Os, like you want us to show that?
No. You could skip to this right here. I'm just trying to illustrate which part I'm going to exclude. But yes, you can jump right over to here. That's fine. Okay, so yes, again, pure solids and liquids, our solids and pure liquids do not appear in our equilibrium expression. They're considered to have constant concentrations, so you're only going to include the aqueous and any gases. All right, and then going back to that equilibrium. With gases, so for the sake of practice, okay, take a second and build me my equilibrium expression here. Okay, so my K equals the concentration of products over concentration of reactants. And I got to square my dinitrogen monoxide because, again, my coefficient becomes an exponent. Oh, shit. Okay, my bad, y'all. If you were confused, it's because I switched these. This should be N4O2. Otherwise, that is not a balanced equation. My bad. All right, so equilibrium with gases, what do we want to make a special note about? These expressions can be expressed in terms of concentration. Right? So just like we've done here, we would call this a Kc because it's in terms of concentration. Or you can express it in pressure. Okay? And it would look the exact same, but you would say the pressure of each one of these gases. And we would call that a Kp. How you build it is the exact same. It's just instead of concentration, you use pressure. So this would be the pressure of N4O2 divided by the pressure of N2O squared. Either one of these would be legit equilibrium expressions for gases, okay? And that's simply because for a gas, the pressure is proportional to the concentration. Those two things are directly proportional. If you double the pressure, you double the concentration. If you cut the pressure by 20%, you've cut the concentration by 20%. Okay? Y'all can trust me. The book does a derivation using the ideal gas law, or y'all can trust me on that. All right? But the bottom line is, since these two are directly proportional with one another, we're allowed to say, define our equilibrium expression either in terms of concentration or pressure. And you'll see either or. All right, so then the last thing, what can we do with these equilibrium expressions? We're going to sort of beat them to death next class with some algebra, but the simplest thing that we can do with this is given the concentration at equilibrium, or given the pressure at equilibrium, we can calculate the value of that equilibrium constant, right? So what do I mean by that? So taking this same example here, if I tell you that at equilibrium, the pressure of N4O2 is 1.25 atm, and the pressure of N2O is 0.75 atm. What is the value of Kp? That was a 7.5. All right, so all we need to do, as long as you got your equilibrium expression, it's very straightforward. You're just going to plug in the values that you got. 1.25 atm divided by my 0.75 atm. The biggest mistake that people make is they forget to include the exponents, right? We built that equilibrium expression from our balanced chemical equation. And because there was a 2 as a coefficient, it became an exponent of 2 in my equilibrium expression. I need to make sure to square that 0.75 then. All right, so you're just plugging in variables. Just don't forget those exponents. That's kind of the most common mistake. Okay, so punch that into my calculator. We're just going to do 2 decimal places here, 2.2. All right, and then your units for K will actually depend on, first of all, if you're talking about concentration or pressure, and it's actually unique to each reaction as well. In this case, everybody take a second and see if you can figure out what my units would be. Not quite. 1 over atm, right? Atm on the top, atm squared on the bottom. So 1 over atm. And you do get weird units like that. Some equilibrium constants are unitless. Other ones are, molarity squared, and other ones are inverse molarity. It sort of really depends on your reaction and how many products versus reactants you have. Cool? All right, so then last thing here, up until now I've been balancing these chemical equations for you just for the interest of time, but 100% I'm assuming that all you Chem 1A graduates know how to balance a friggin' chemical equation, right? So let's just do one with an unbalanced chemical equation where you're going to give me this equilibrium expression. And actually, you guys can give me the Kp. All right, Kp means I'm going to do this in terms of pressure, but again, I got to balance my chemical equation before I can construct my equilibrium expression, right? And although my phosphoruses are balanced as is, I can see that there's an imbalance in the number of chlorines, okay? The only way that I can correct this is if I put a 2 out front here and a 3 out front there to make them both 6. I'll have to adjust my phosphoruses as well. So that's my balanced chemical equation. Then I'm going to put products over reactants. Again, since it's Kp, I'm going to do the pressure of phosphorus trichloride, and it'll be squared divided by the pressure of that Cl2 cubed. And then am I going to include this at all in my equilibrium expression? No, why's that? Because it's a solid, so I just don't have to worry about it. All right? So this would be the equilibrium expression in terms of pressure, the Kp, for this particular reaction. Cool? All right, bring your calculators next class. We're going to be doing some algebra.